we'll be going with this rotation revision. So I'll be starting with moment of inertia and I'll be going on to like remaining stuff. But yeah, as rotation is a big chapter, you can't expect me to go in detail. I'll be just, the notes is also not perfect maybe because I didn't get time to like revisit it or like modify it. So whatever I have, I'll be going in sequence. This is how I plan my sequence. Maybe I'll be adding some stuff in between extra later. So if someone has suggestions after this, maybe you can let me know so that I can include them for whatever, my next classes, right? So first what I try to do is I try to define moment of inertia for point mass. It is m into perpendicular distance square about an axis. So I have taken one point here at a distance, mass is 1 kg, this coordinates are 3, 4, 0. Thereafter I found moment of inertia about x axis, about y axis, about z axis, and yeah, about passing through this point, okay, x axis, y axis, z axis. So thereafter I have, yeah, you can see that 16 plus 9 is 25. It is not going to be like by luck, it will be happening every time. Now here you can see 100, 64 plus 36 is 100. Now what is the difference between these two? I just made the distances twice. If I made the distance twice, moment of inertia is becoming 4 times, which you can expect because moment of inertia dimensions are ml square, right? Now similarly in the next question what I did, I kept the distances same but I changed the mass twice. If I change the mass twice, then what will happen to the moment of inertia? It will become twice, which you can expect. Thereafter I kept 2 things and total moment of inertia. Again you can see 80 plus 45, 125. Ix plus Iy is going to be Iz. So that is perpendicular axis theorem. We will be going to prove it later. Now after that I will be going on to this question where there are 4 point masses and you need to find moment of inertia about this axis. So for this one it is m1 r square, m2 r square, m3 r square, m4 r square, right? So totally it will be m1 plus m2 plus m3 plus m4 into r square. Now based on this I will be going with derivation of moment of inertia of a ring about this axis. So ring I can visualize like many points. So for one point it is m1 r square, m2 r square, m3 r square. So when I add all those, what I will be getting? Total mass into r square. Now similarly I can prove the same thing for any part of the ring. Now if half ring has mass m, then its moment of inertia will be m r square about this axis. Thereafter based on moment of inertia of a ring, I will be deriving moment of inertia of a disc by taking ring element. Moment of inertia of ring is m r square, m of ring is this much, so you will be integrating, you will be getting moment of inertia of the disc is m r square by 2. Now if moment of inertia of this full disc whose mass is m is m r square by 2 about this axis, then I need to find about for half disc about this axis. So for half disc, if the moment of inertia is I, then for this half disc also moment of inertia is I, because if I rotate it by 90 degrees I will be getting this one. So mass distribution is not changing. Let me say there is some point mass here at a distance some r, some z. So if you rotate it also, the distance between this axis and that point is not going to change. So mass from here to here, mass distribution is not going to change about the axis. So if the moment of inertia about this axis is I, moment of inertia about this axis is also I. Now if I club these two figures, what I will be getting? I will be getting a disc of total mass m plus m, 2m. So what is the moment of inertia of disc of mass 2m? 2m into r square by 2. But what is that? That is summation of these two moment of inertia, I plus I. So I will be m r square by 2. The other way of looking at it is, if there is a disc of mass m, break it into 2 parts. So this will become m by 2, this will become m by 2. Now rotate it and keep it on top of the other half disc. So it will become m by 2 plus m by 2 m. You are not changing any mass distribution, so moment of inertia is not going to change. So whatever it is, from there you can go with, if I divide the disc into 6 sectors, so what is the moment of inertia of one sector? If the sector mass is m, then the total mass will be 6m. You can similarly prove that it will be m r square by 2. Now rod moment of inertia about this axis, so what you will be doing, you will be taking some element, you will be finding the moment of inertia of that element and you will be integrating, you will be getting the result as ml square by 3. Now that is about the end. Now about center of mass, you will be doing the same thing, you will be just the limits will be the only variation. So you will be getting ml square by 12, you must be knowing these results. Now there is a thing, moment of inertia of rod about center, we got it as ml square by 12. Now what I can do, this big rod of length L and axis is at the center, I can visualize it like two separate rods whose mass is m by 2 and length is L by 2, and the axis is end of the small rods. I can look at the same figure like this for moment of inertia, because if I move up or down, moment of inertia won't change because mass distribution about this axis is not going to change. So whatever moment of inertia of this one must be same as moment of inertia of this one, that you can see. Now moment of inertia of rod about the end is m L square by 3, m L square by 3. Now for this one also it is m L square by 3. So when you add these two, you will be getting m L square by 12, which must be matching with this one. Yes, obviously. Now the next one is moment of inertia of hollow sphere. So what I will be doing is I will be taking some point. If I will be finding moment of inertia of that point about x-axis. If I want to find a moment of inertia about x-axis, the only perpendicular distance matters, right? So for that only y-coordinate and z-coordinate matters. So moment of inertia of some point about x-axis will be that mass into y square plus z square of that particular mass coordinate, right? Now similarly, moment of inertia about y-axis will be this much, about z-axis will be this much. This is for one single point. So if I want to find for all such points, what I need to do, I need to add them. So if I add all these three, what I will be getting? Ix plus Iy plus Iz. Ix plus Iy plus Iz. So right hand side, what I will be getting? M into x square will be coming twice, y square will be coming twice, z square will be coming twice. So totally it will become 2 times of this thing. Now what is this? For a hollow sphere, it is radius square, right? X square plus y square plus z square is r square, right? So this one I can write it as r square, right? Now what about this? It is symmetrical. So moment of inertia about x-axis and y-axis and z-axis must be same. So I can call these three are same. So the total will become 3i. So I will be 2 by 3 m r square. This is the, slightly easier way, or we are trying to avoid the integration, right? Now based on this result, we will be deriving for solid sphere. Solid sphere, we will be visualizing like many hollow spheres, and you will be finding moment of inertia of one hollow sphere, and you will be integrating, you will be getting moment of inertia of solid sphere. Thereafter, this was an example just to show moment of inertia of rod about this axis is going to be 0, because rod in the sense we will be talking like it is one dimension. So every point is on the axis, distance is 0, perpendicular distance is 0, so moment of inertia is 0. Moment of inertia of rod about this axis will be 0. About this axis it is ml square by 3, right? Now similarly, I have taken one more example here. There are 4 rods. You want to find the moment of inertia of this system about this axis. So this rod moment of inertia will be 0. This rod moment of inertia is ml square by 3, because this axis is end of this rod. Now for this one also it is ml square by 3. Now for this one you can see it was not kind of regular question, but what you can see if you take one mass here, that is at a distance L. If you take the other point mass, that is also at a distance L. So if you take one mass, the moment of inertia will be m1 L square, m2 L square, m3 L square, m4 L square. So when you add all such, what you will be getting? Total m into L square. So moment of inertia of this rod about this axis will be m into L square. So 0 plus ml square by 3 plus ml square plus ml square by 3, you will be getting 5 by 3 ml square. Now hollow cylinder, moment of inertia of hollow cylinder about this axis will be same as ring. You can do it in 2 ways. One is like you can take one ring of mass m1, then moment of inertia of that ring is m1 r square. So if you take one more ring, m2 r square. If you take one more ring, m3 r square. So when you add all such things, what you will be getting? Total mass into r square. The same logic applies here also. You can take discs, m1 r square by 2, m2 r square by 2, m3 r square by 2, and so on. Or some people can say like, even if you compress it, moment of inertia about this axis is not going to change. Even if you compress it, moment of inertia about this axis is not going to change. So which will be same as ring of mass m, which will be same as disc of mass m. Now the next one, there is a rectangular lamina. So you want to find the moment of inertia about this axis. Now what you can do, you can take one rod, different rods. So m1 for this rod, moment of inertia will be m1 b square by 12. m2 b square by 12, m3 b square by 12. So when you add all such, you will be getting total m into b square by 12. The other way of saying it is, even if you compress it this way, moment of inertia is not going to change about this axis, which is mb square by 12, like a rod, right? If you compress it and make it a single rod of length b, then moment of inertia will be mb square 12. By the same logic, you can say m1 L square by 12, m2 L square by 12, m3 L square by 12. So when you add all such, you will be getting ml square by 12. Or if you compress it this way, you will be getting a rod of length L. So moment of inertia will be ml square by 12. Now hollow cone, you will be taking some element, and you will be finding the moment of inertia of that element, and you will be integrating. That is up to you. Now while integrating, what I did is I modified the equation. When I modified, I ended up somewhere here. Now this one, if I want to see, it looks like this. If there was a disk of mass m, then if I take some ring of radius r, and if I try to find the moment of inertia of that ring, yeah, this equation looks like as if I have taken some disk and I wanted to find the moment of inertia of that disk using some ring. So basically the result will turn out to be like disk, right? Like disk. You can see the result will be turning out to be like disk. So what you can see, like if there is a hollow cone, if you press from the top, it will be forming a kind of disk, and moment of inertia is, while solving, you can see like it is coming out to be like disk integration itself, right? So you can remember the result easily that way. Now solid cone, again you will be integrating it, that I am not going to do. Now, okay, till now we didn't do anything. Till now we didn't use any other thing other than the definition of moment of inertia, that is mass into perpendicular distance square about the axis. This is the first time we are doing something other than the definition of moment of inertia, that is perpendicular axis theorem. Now, if it is a planar object, the first thing is it must be planar object, and if you take some axis like x-axis, y-axis, anywhere, and if you take some points moment of inertia about x-axis, then it will be dm into perpendicular distance square, which is y square. Now if you take about this axis, it is dm into this distance square, which is dm into x square. So when you add these two, or if you want to find about z axis, but passing through this point, then it will be dm into this distance square, which is, this distance is root of x square plus y square, so that distance square will be x square plus y square. Now when you expand it, you will be getting this one. Now this is nothing but this term, this is nothing but this term, so iz equal to iy plus ix. Now how we are going to apply it? It's like, if it is a planar object and if you take any two mutually perpendicular axes in the same plane, then moment, and you can see there will be some intersection point. So if you want to find the moment of inertia about this axis, then that will be summation of moment of inertia about this axis plus this axis. Any two mutually perpendicular you can take, it need not pass through center of mass, right? I didn't talk anything about center of mass. So any two mutually perpendicular axes you can take, then the moment of inertia about this axis will be same as summation of this plus this. So that's the statement. Now I am going to use it. What I know some information like moment of inertia of ring about this axis is mr square by 2. I have shown it earlier. Now based on this, I want to find moment of inertia of ring about this axis. I know about this axis it is mr square by 2, so I want to find about this axis, how much will be that. Now what I can say, by symmetry, or like, yeah, whatever it is, if the moment of inertia of ring about this axis is I, then the moment of inertia of ring about this axis also will be I. Any axis it will be I only. You can see like it is highly symmetrical figure. So if moment of inertia of ring about this axis is I, then about this axis also will be I, about any axis will be I. But what I will be doing, I will be choosing this as one axis and this as other axis, because I know perpendicular axis theorem. So if this moment of inertia is I, then this moment of inertia also will be I. Then what will be the moment of inertia about this axis, which it will be I plus I, 2I. But what I know, 2I is nothing but mr square. 2I is nothing but mr square, so I will be mr square by 2. Now by going with the same logic for the disk, about this axis it is mr square by 2, so about this axis it will be mr square by 4. For a rectangular lamina, about this axis it is mb square by 12, about this axis it is ml square by 12, so about this axis it will be m into b square by 12 plus L square m into L square by 12. Now we are going to make square lamina out of rectangle. So for a square lamina about this axis it is ma square by 12, about this axis it is ma square by 12. So about this axis it will become how much? This plus this, which will be ma square by 6. Ma square by 6. Now if someone asks you what is the moment of inertia of square lamina about this axis, which we didn't derive earlier, what we derived earlier, we have seen like this moment of inertia is ml square by 12. How we can get it? We can compress it, or we can say like it is many strips. And similarly, how we got this as ml square by 12, either you can compress it or you can see it like many strips. Now what we know moment of inertia about this axis is ma square by 6, but they are asking about this axis. Now what I can do, I can construct one more axis which is perpendicular to it, If moment of inertia about this axis is I, you can see, then if you take this axis, then you can see again two triangles which are similar. So moment of inertia, if moment of inertia about this axis is I, then about this axis also will be I. So I plus I, yeah, in a square diagonals will be perpendicular. So I can apply perpendicular axis theorem. So if this moment of inertia is I, this is I, then the moment of inertia about this axis will be 2I. 2I equal to ma square by 6, so I will be ma square by 12. Now similarly, if not diagonal, if they give some other axis, what you can do, when they gave this axis, you have found this axis is perpendicular. When they gave one diagonal, you found the other diagonal is perpendicular. Now when they give some this axis, you can find other axis which is perpendicular, like the other axis will be like this, Now you can draw the second figure and you can see by yourself. If moment of inertia about this one is I, there you will be getting two figures, right? So when you draw one axis, you can see the similar kind of figures will be coming here. So the meaning is, if moment of inertia about this axis is I, you can find other axis which is perpendicular to this and passing through this point such that the figure looks same, or moment of inertia about this axis also will be I. That's the important thing here. That happens only for square, not for rectangle, right? So if moment of inertia of square about this axis is I, you can find one more axis which is perpendicular to this, which looks exactly same, the figures looks exactly same. So if moment of inertia about this axis is I, then the moment of inertia about this axis also will be I. So I plus I, it must be 2I. 2I is ma square by 6, so I is ma square by 12. So from here what we concluded? We concluded, if there is a square lamina, no matter which axis you take, if it is passing through the center of mass, no matter which axis you take, if it is passing through center of mass, then the moment of inertia about that axis will be ma square by 12. So no matter which axis you take in the same plane, but passing through center of mass, its moment of inertia will be ma square by 12. Now if someone asks you what is the moment of inertia of this right angle triangle about this axis where this mass is m, so what I can do, I can construct back square. Now if this mass is m, then square's mass will be 2m. Moment of inertia of this square about this axis will be its mass times a square by 12. So that is the moment of inertia of square. But what I need only half of it, because you can see both are similar structures. So if this moment of inertia is I, then this moment of inertia will also be I. So I plus I, 2I. 2I is this much, so I will be how much? ma square by 12. Now why I am doing this here is because I know some property which I will be showing you later. Moment of inertia of triangle about the base depends only on the height. That will be difficult for integration, but you can quickly get it back from here. Next, parallax theorem. I am not going to explain it much. So parallax theorem, if you know the moment of inertia about center of mass, then about any axis, if you know moment of inertia about axis passing through center of mass, then moment of inertia about any axis parallel to that particular center of mass axis will be given by moment of inertia about center of mass plus m into that perpendicular distance square. Now we know moment of inertia of ring about this axis is mr square. So if someone asks you to find moment of inertia about this axis, then it is IC plus m into this distance square. So that is mr square plus mr square, which is 2mr square. And note that parallax theorem can, there is no restriction like it has to planar body, right? So parallax theorem you can apply anywhere, but perpendicular axis theorem, be careful, you have to apply for planar body only. Now moment of inertia of ring about this axis, we know mr square by 2. If someone asks you about this axis, what I can say, it is IC. You need to understand these two axes must be parallel. So if you want to find about this axis, then you need to take one more parallel axis which is passing through center. So that is mr square by 2 plus m into this perpendicular distance square, which is r square. So mr square by 2 plus mr square, which is 3 by 2 mr square. Now what we did, we used the definition of moment of inertia. Thereafter we have seen some examples. Anyway, if I leave out the examples, we have seen the definition of moment of inertia. We understood moment of inertia depends on the mass distribution about the axis. Thereafter we have seen perpendicular axis theorem and we have seen parallel axis theorem. So these are the only three things there in moment of inertia. Right, now what we are going to do is, we are trying to avoid integration and we are trying to see some questions how we can do without integration. Now but for that, what you need to know is dimensions of moment of inertia must be ml square. That you need to know, and you need to know perpendicular axis theorem and you need to know parallel axis theorem, right? So now going with that, you need to know the definition of moment of inertia also, which is mass, it depends on the mass distribution. And this question we have already seen. If there is a rod of length L, if you want to find the moment of inertia about this axis, we have used integration back then. Now we will try to see without integration. Now if this moment of inertia about the axis which is passing through the center is I. Now what I will be doing, I will be breaking this one into two parts. first part, second part. Now moment of inertia of this system about this red axis must be same as moment of inertia of this system about this red axis plus moment of inertia of this system about this red axis. Now my aim is to find I. Now if this is I, now this is the important thing. If moment of inertia of this rod about its center is I, then moment of inertia of this rod about this center will be I by 8. Now why it is moment of inertia will be like some constant value into ml square. That constant doesn't vary because it is a rod and this is center, this is a rod and this is center, so that constant is not going to change. So what is the only thing that changes from this situation to this situation? That mass and dimensions. Mass became half, length became half, so moment of inertia will become 1 by 8 because moment of inertia will be of dimensions ml square. So 1 by 2 into 1 by 2 whole square, which will be 1 by 8. So if this moment of inertia is I, then this moment of inertia will be I by 8. So then this moment of inertia also will be I by 8. Now if this moment of inertia is I by 8, by applying parallel axis theorem, I can say moment of inertia about this axis will be I by 8 plus m into perpendicular distance square. Perpendicular distance is L by 4 and its mass is m by 2. So if I want to find moment of inertia about this axis, it is IC plus its mass into this distance square. So similarly I can say this one also it will be I by 8 plus m by 2 into L by 4 whole square. Now if I want to find the moment of inertia of this one, what I need to do? I can say it is summation of this one plus this one. So what will be the summation of these two on right hand side? It will turn out to be, when I add it, I will be getting I by 4 plus ml square by 16. So when I find moment of inertia using right hand figures, I will be getting I by 4 plus ml square by 16. But I know it must be equal to I. So from left hand side figure, it is I, but from right hand side figure when I calculated, I got it as I by 4 plus ml square by 16, but those two must be equal. So from here when you modify it, you will be getting I equal to ml square by 12, which is as expected because you know the answer already. So what we did here, we didn't do any integration. All we did is we understood the definition of moment of inertia and we understood the dimensions of moment of inertia and we used parallel axis theorem. We didn't apply perpendicular axis theorem here, we applied only parallel axis theorem. Now going to the next question, there is a square. Now you need to find moment of inertia about this axis. Now assume that you forgot all the information other than definition of moment of inertia and parallel axis theorem and perpendicular axis theorem. Now what I will be doing is I will be looking at this big square as 4 small squares. Now if this moment of inertia is I, then moment of inertia of this small square about this axis will be I by 16. The reason is if this mass is m, then this mass is becoming m by 4, and if this length is L, this length is becoming L by 2. So mass is becoming 1/4, length is becoming half. So moment of inertia will become 1 by 4 into 1 by 2 square, which is 1 by 16. Mass is becoming 1/4, length is becoming half. Now if this moment of inertia is I by 16, then moment of inertia of this structure about this axis will be I by 16 plus m into, mass is m by 4 into this distance, which is a by 2 root 2 square. I applied parallel axis theorem from here to here. So if this moment of inertia is I, then this will be I by 16, then by applying parallel axis theorem I will be getting this much. Now but how many such squares are there? There are 4 such squares. So moment of inertia of this entire structure, moment of inertia of this square about this one, of this square about this one, of this square about this one, of this square about this one. When I add all 4, I must be getting moment of inertia of the initial structure. So when I do this, 4 into I by 16 plus this thing will be equal to I. So when I do it, when I solve it, I will be getting ma square by 6, which we already know. Now the next question, which we don't know. Now we have done 2 questions which we have already know, and yeah, we kind of understood how to use it. Now we are going to do for something which we don't know. Of equilateral triangular lamina whose total mass is m and whose side length is a. Now you need to find moment of inertia about this axis. Now what I can do, I can divide this one equilateral triangle into 4 equilateral triangles. 1, 2, 3, 4. Now okay, I don't know how many colors you can see that, but when I zoom it, it looks like this. There are 4 colors. I will be I think they will be uploading PDF. So now the thing is, what is happening to the mass of any one triangle? Let me say this triangle. One big triangle is broken into 4 parts. So mass is becoming 1/4. What is happening to the length? If this length is a, then this length of triangle is going to be a by 2. Mass is becoming 1/4, length is becoming half. So moment of inertia will become 1 by 16. So if moment of inertia of this structure about this axis is I, then moment of inertia of this equilateral triangle about this axis, about its center axis will be I by 16. This triangle about its center axis will be I by 16. This triangle about its center axis will be I by 16. This triangle about the center axis will be I by 16. But what I need to find about this particular axis. The meaning is this particular axis, which is the center of this small square or center of this big square. Center of this big square will be same as center of this small square. So moment of inertia contribution of this blue color thing will be I by 16 only. But about red, for red triangle we know moment of inertia about this axis is I by 16. So if I want to find moment of inertia about this axis, what I need to do, I need to apply parallel axis theorem, which is its mass m by 4 into this distance square. So moment of inertia of blue triangle about this axis will be I by 16. Of this triangle about this axis will be I by 16 plus parallel axis theorem. This triangle will be I by 16 plus parallel axis theorem. This triangle will be I by 16 plus parallel axis theorem. These three are similar to each other, so you can say like 3 times of any individual, that's also fine. That is from right hand side. So from left hand side it must be equal to I. So when you solve it, you will be getting ma square by 12. Ma square by 12. Right? Now radius of gyration, okay. So if there are two rings of mass m and radius r and mass 2m and radius 2r, if you want to find the moment of inertia about this axis, then it is mr square plus 2m into 2r square. Okay, I think it is, I have taken disk. Okay, I have taken disk. So if it is a disk, then it is mr square by 2 plus 2m into 2r whole square by 2. So when you add that, you will be getting 9m into r square by 2. Now the question is, if you want to replace this entire structure with a single mass of 3m, if you want to replace this entire structure with a single mass 3m, m plus 2m, that is 3m. If you want to replace this entire structure with a single mass which is equal to the mass of the system, that is 3m, where you will be placing it so that the moment of inertia will become 9m r square by 2. So where you will be placing the total mass 3m, point mass 3m, so that moment of inertia of this structure will be same as this structure. You will be getting, that is root of 3 by 2 r. That is the radius of gyration of this particular figure. So radius of gyration in the sense, if you want to replace the total mass with a point mass, where you will be placing it, you need to find that distance. Now the next question, moment of inertia of triangle about an axis along the base. So when you integrate it, you will be getting, when you do that, you will be getting 1 by 6 m h square, where h is the height, So moment of inertia of triangle depends about the base depends only on the height. So whether it is this triangle or some other triangle, if the height is same, then moment of inertia of all those triangles will be same. So yeah, obviously you can see here. Okay, if you don't understand, I have written like, is there any easy way to prove it? Because when the result is such simple, generally there must be some other easy way to see it. I couldn't see it there, but that doesn't mean it's not there. There will be some other easy way to see it, but I didn't find it yet. Right. So now moment of inertia of any triangle about axis depends only on the perpendicular. Height. We concluded that. Now, if you can't remember the result, or if you, derivation is obviously like little difficult. So how to get it back? Is, I have used something earlier. Moment of inertia of this triangle, if I want to find, I can make it a square and I can find total moment of inertia is 2i, which will be equal to this thing. So moment of inertia of this triangle will turn out to be ma square by 12. Now how I can write it? I can write it as this mass times this perpendicular distance square, mass times that perpendicular distance square, that height square. So when I do that, 1 by 6 factor will be coming out. So you can look at this one like 1 by 6 times mass times this height square. So from there I can get it back easily. If I know the result, I can get it back easily. Right? Now I will be going on to definition of torque, angular momentum. So torque is defined as r bar cross f bar, right? If force is applied at some particular point, and I think there is no need of explanation. So you can just look into. Angular momentum is r bar cross p bar, which is r bar cross mv bar. When I differentiate it, I will be getting two terms. Now this is v bar cross v bar is 0. So you will be getting rate of change of angular momentum will be r bar cross f bar, which is nothing but torque. So torque will change the angular momentum. That's what you will be knowing. Now if there is some particular point where you are applying a force in this direction, where if you want to calculate torque about this particular point, torque and angular momentum will be calculated about particular point. So I am calculating about this particular point. So about this particular point. So when I calculate torque about this particular point, magnitude, how I will be getting torque magnitude is R into F into sine of angle between them, that is R into F into sin theta. What about the direction? Place your fingers along first vector R bar and curl your fingers towards F bar. So this is the direction of torque. This is the direction of torque. So when I tried to find about this point, I concluded direction of torque is this direction. Now how you can see that? Sometimes what people will do, like R into F into sin theta, how they will try to visualize it? They will resolve that position vector into two components, R sin theta and R cos theta. R sin theta and R cos theta, and they will select perpendicular distance times F, perpendicular distance times F, because cross product of these two only will survive, cross product of these two won't survive. So R sin theta into F, that is the magnitude they will say. Some people, what they will do, they will keep the position vector same, they will resolve the force into two components, or along and perpendicular. Again, cross product of these two will be 0, so they will be saying it is R into F sin theta. So whether it is R sin theta into F or R into F sin theta, you can visualize in both ways. Now, there have been, I need to include some easy examples here because that will be the, very beginning of the chapter. So, now for a small example, if there is a point mass here and you are applying a force at an angle 30 degrees to this line where you are finding torque about this particular point, then what will be the torque? What I can do, I can resolve this force into two components, F root 3 by 2, F by 2. Now, this won't be providing any torque because R bar cross F bar will be 0 because along the same line. So there will be torque only because of this one, which is L into F by 2, L into F by 2. Some people, what they do is, they will keep the force same, they will keep the force direction same, but they will resolve this L into two components, which is, one is perpendicular component L by 2, one is parallel component L root 3 by 2. So this won't be providing any torque because R bar cross F bar will be 0, so torque will be because of only this, which is L by 2 into F. So you can visualize it anyway, I am not going into that, that's not much necessary. So similarly, when I take some example, there is a force applied here for point mass, you want to find the torque about this particular point. So what you can do, you can resolve this one into two components, one is perpendicular, one is parallel. So perpendicular distance times 1, so 3 by 5 into 1, which is 3 by 5. The other way of doing it is, some people will keep the force, or will keep the position vector same, and they can resolve the force, which is force is 1, so when you resolve, you will be getting 3 by 5 and 4 by 5, this won't be playing any role in torque. So 3 by 5 into 1, which will be 3 by 5. Now this is some example from projectile. So if you are projecting at an angle 45 degrees with a speed 20 root 2, at maximum height its velocity will be horizontal velocity 20, and this maximum height you can calculate 20. This distance you can calculate as 40, mass is given as 1 kg in the question. So at this particular point, what is the angular momentum if you calculate about at this particular position, what is the angular momentum of that mass about this point? So for that, what you need, this perpendicular distance. Actually you have to drop position vector and you have to resolve it, but what way I will be doing, I will be taking this perpendicular distance and I will be multiplying with 20. So 20 into 20 will be 400, right? M R perpendicular distance times M into V, M into V. So I will be getting 400, and what is the direction? Direction is into, angular momentum direction is into. And what about the torque? If I want to calculate the torque, R bar cross mg, R bar cross mg. But if I want to find only magnitude, then what I can do, I can take perpendicular distance. Sorry, this is not the perpendicular distance, this is the perpendicular. Mg is going this way, so perpendicular distance is this one, which is 40 into mg. 40 into mg, which is 400. Again, what is the direction? R bar cross mg, R bar cross mg, which is into the board. Now, there is some massless string and there is some bob. If you generally leave it, it will be like in this position, but what I am doing, I pulled with some force and now it is in equilibrium. Now, what is that force? When you know this angle is theta, when you know this angle is theta, when you know the mass of the bob is m and angle is theta, what will be that particular force, or else what force you need to apply so that this angle will become 45, that way you can see it. So what I can do, generally you must have seen this in Newton's laws, you will be making net force is 0. So you will be resolving T cos theta equal to mg, T sin theta equal to F, and you will be doing. Now I am just making it the other way. Now if it is in equilibrium, then net force must be 0, net torque must be 0. Now that's the thing. Equilibrium means it must be in translational equilibrium as well as rotational equilibrium. Net force must be 0, net torque must be 0. Now net torque must be 0 about, that I will show later, about any point it must be 0, but I will be taking about this point. If I take about this point, the good thing about this point is torque due to tension will become 0. Torque due to tension will become 0. So the meaning is torque due to mg must be balanced by torque due to applied force. So torque due to mg will be in which direction? Now how to get that? So I will be extending this line. Now this is the perpendicular distance. Perpendicular distance is L sin theta. L sin theta into mg will be the torque because of weight. Now torque because of this force I can extend it. This is L cos theta. L cos theta into F. That is the torque because of this force. But what about the directions? Torque because of this force will be R bar cross F bar. It is in this direction, which is positive K cap I have taken. Torque due to mg is R bar cross mg bar, which is into I have taken negative. So net torque must be equal to 0. So from there I will be getting mg tan theta. I could have got that by many other ways using Newton's laws also, right? Now the next thing is torque due to internal forces. Internal forces in the sense action and reaction kind of forces. Now I have taken two particles here. M1, M2. This position vector is R1 bar, this position vector is R2 bar. Now if there is internal force, this is the internal force because of M2 on M1. Now this is the reaction force on second mass due to first mass, right? Now I need to show torque because of these two, summation will be 0. Now if I take torque because of this force, that will turn out to be how much? R1 bar cross F12 bar. Now if I take torque because of this force, then it will be R2 bar cross M2 bar, about this particular point, right? R2 bar cross F2 bar. Now F21 bar is nothing but negative of F12 bar. Now I can take F12 common. I will be getting R1 bar minus R2 bar, which is R12 bar. R12 bar, okay, R1 bar minus R2 bar. This is R1 bar. Okay, that is going to be this direction, right? Yes, that is going to be this direction. This vector is nothing but this direction. That is position of first vector with position of first mass with respect to second mass. Position of first mass with respect to second mass. Now you can see these two directions will be same or maybe 180 degrees. So if it is, so then it has to be 0. So if the internal forces are action and reaction type forces, then torque due to internal forces will be 0. Torque due to internal forces will be 0. This is one important thing. Sometimes we may use it unknowingly, but yeah, you need to know it is valid. Now what we did, obviously like this is the same thing we will be following in almost all the chapters. We will define for 2 point masses, or we will define for point masses, then we will go for accident objects. So you can see like this is the situation from the very beginning of whatever you are learning in physics. Now in this particular chapter we define moment of inertia of point masses, thereafter we went for rigid bodies. Now here we defined torque and angular momentum if there is point mass. Now we are going to extend it if there are many masses, many point masses, thereafter we will go for like continuous body or rigid body. Now total torque of the system is defined as torque on individual masses. So that is R1 bar. Now if there is only one mass, if there is some particular mass, ith mass, then position vector cross force acting on it. Position vector cross force acting on it. Now that force consists of external forces and internal forces. So I can divide into two parts, but there is summation. I need to add all such things. So torque due to internal force won't be 0 on one particular point, but if you take the entire system together, if you take that sigma together, it will turn out to be 0, which we have seen it. So torque will turn out to be just because of only external forces, which we have already seen. Anyway, so this says the same thing, angular momentum of the system equal to angular momentum of summation of and angular momentum of individual particles. So it's that I just modified it. So what I did here, I am trying to see what is the differentiation of this angular momentum. So there are two terms which are varying, so I can differentiate it. I will be getting two terms. Now this term will turn out to be 0 because V1 bar cross V1 bar is 0. So here you will be getting sigma Ri Fi. So when you do it, the result, now the result is important. What is the result? Even if it is for single point mass, we have seen rate of change of angular momentum equal to torque. Even for system of mass also, it is turning out to be the same. So which you may be thinking that it's obvious. Okay, that's fine. Thereafter, okay, what we did, we found for point masses we defined the definition of torque and angular momentum. Thereafter we have seen for different point masses, point system with point masses. Now we are going for rigid body. So when you do for rigid body, what will happen is the torque will turn out to be I alpha form. Torque will turn out to be I alpha form. Angular momentum will turn out to be I omega form. So similarly, if you want to see kinetic energy about some fixed axis. If some rigid body is rotating about fixed axis, then kinetic energy of one particle will be half m1 v1 square. All such particles will be summation of that. But if some particular body is rotating about some axis, you can see like it will be performing circular motion. When it is performing circular motion, you can see velocity will be r omega. So when you modify it, you will be getting half into I into omega square. What is that I? That I is moment of inertia about that particular axis, which is about which the body is rotating, Thereafter, you can see like the rate at which the kinetic energy is changing. When you do that, you will be getting something like tau d theta. So some people will say like instead of f into dx, you can use tau into d theta to see work done. Some people will say like it is rotational work done, but I prefer work done definition as f bar dot ds bar itself, where f bar is the total force acting there and s bar is the displacement of that particular point where we are applying force. Anyway. So we'll be just seeing how to use it. Now if there is a rigid body which is fixed about this axis, now I am continuously applying force perpendicularly only. So force, I am changing my force direction according to the rod such that it will always be perpendicular. So what is the torque at this particular position? That equal to, okay, torque is this L into F. Now that equal to I alpha, which we have seen. What is I? I about this axis, because we are taking torque about this axis. Torque about this axis equal to, now you can see, when I take torque about this point, I understood that it will be coming about this axis. So torque about this point will be same as torque about this axis in this particular question, that equal to I about this axis into alpha. Now I about this axis is ml square by 3 into alpha. So alpha will be 3f by ml. Now the other definition I know is torque for system of torque for single mass or point masses system or rigid body system, it must be equal to rate of change of angular momentum. So torque about that particular point, or in this particular question it is about this axis, equal to rate of change of angular momentum about this axis. So when I bring this dt this side, I will be getting tau dt equal to dl bar. Now some people will say like this is angular impulse equal to change in angular momentum. Generally, yeah, angular impulse equal to change in angular momentum. Some people will say that. Now what is torque? Torque is L into F dt, that equal to change in angular momentum, final angular momentum minus initial angular momentum. Final angular momentum is I into omega. So when you do that, this L into F are constant. So when you take it out, you will be getting omega equal to 3f by ml, which you know, because it is constant acceleration, so omega equal to omega naught plus alpha t, or if you differentiate this, you will be getting angular acceleration as 3f by ml into t. Whatever it is, whichever method it is. I mean, I just used this one so that I can introduce angular impulse term here. That's all. Now, angular momentum in this particular case turned out to be how much? Moment of inertia about that particular axis ml square by 3 into omega. What about kinetic energy? Kinetic energy we didn't do, but by definition, we have just seen like some kind of proof earlier. It will turn out to be what way? It will turn out to be half into moment of inertia about that particular axis into omega square. So half into moment of inertia of that particular axis into omega square, where that axis is fixed in this particular question. Now there is a rod which is fixed here, whose mass is m and length is l. There is other point mass which is coming with a velocity u, and it is hitting and it is sticking. Now after this, with what angular velocity the rod will rotate? Now this is the question. Now we can't use conservation of momentum because there is collision happening. Those are internal forces. Now both weights will be there, but those are in vertical direction. Okay, anyway, weights won't be creating impulse because weights are constant forces. Constant forces won't create impulse because that collision is happening for a small time. So mg dt will be impulse. That mg is finite value, that dt is very small value. When you multiply finite value with a very small value, you will be getting almost 0, very small value. So impulse due to weights, I won't be worried during collisions. But there is a problem, there is hinge here, so it can exert forces in horizontal direction and vertical. I mean, it can exert force in any direction. We don't know when we don't know the direction, we will say like it will be in some random direction. So we can resolve it into two perpendicular components. One is along x-axis and one is along y-axis. That's what we will be doing. So we can't use conservation of momentum. It's not because of internal force. It's not because of weight. It's because of hinge can exert some external force on my system. What is my system? This rod plus this mass. My system is this rod plus this mass, so the collision force will be internal force. And weight won't be impulsive, but there is some external force on my system. But what I can do? I can take conservation of angular momentum over this point, because during collision internal force torque due to internal force is 0. Apart from that, I won't be worried about weights because angular impulse due to weights also will be negligible. And in this particular question, that will be passing through that hinge, so it will be 0 also, even if you want to consider, but it will be negligible, you don't have to bother. Now there are other external forces. What are those? Hinge forces. Torque due to hinge forces is going to be 0 because perpendicular distance is 0. So that is the reason I can go with angular impulse about this particular point. So I mean torque about this particular point is going to be 0. Torque due to internal forces is 0. Torque due to weight is 0. I mean our angular impulse is 0, so you don't have to bother much. Torque due to hinge forces will be 0. So angular momentum just before collision will be same as angular momentum just after collision, but not throughout, because while it is going this way, weight will be creating some angular impulse for a long time. So during a short moment, angular impulse due to weight can be negligible, but during a good period of time, then you can't neglect it. So just before and just after you can conserve angular momentum. So initial angular momentum equal to final angular momentum. Initial angular momentum is how much? Initial angular momentum for the rod is 0. For the mass it is L into mu. Now that equal to final angular momentum. What is the final angular momentum about this axis? It is I into omega. Now I of the rod is ml square by 3. I of this point mass is ml square. So ml square by 3 for rod, ml square by for point mass into omega, I into omega. So from there you will be getting omega. Yes. So torque is defined as r bar cross f bar into dt generally. So when the force is finite value, and if this t is very small value, very small value, then it will tend to 0. So that is the reason we won't be bothered about angular impulse due to weight generally. Now torque due to weight. If there is a rigid body, it need not be rigid body, it can be anything. Okay, but still we will be going for rigid body. So if you want to find the torque of this rigid body about this particular point, what you will be doing? You will be taking different point masses and you will be seeing what is the torque on each point mass because of the external force only. Now there will be internal forces, but we know torque due to internal forces is 0. Anyway, that doesn't matter for this question. Now I am bothered about only torque because of weights. So torque because of this weight will be r1 bar cross m1g. Torque because of this weight will be r2 bar cross m2g bar, right? So all such torques if you wanted, r1 bar cross m1g bar, r2 bar cross m2g bar, r3 bar cross m3g bar, and so on. So I can put it like sigma of that. Now what I can do, I can bring this one m1 here, and this g bar is a constant value. So summation of this entire thing will be same as summation of this first term cross this second term. I can do it this way. Now what is this? This is m1 r1 plus m2 r2 plus m3 r3, that is total mass into position vector of center of mass. Now again I will be bringing this mass to this side. So I can see the equation is looking like rc bar cross mg bar. Now how I can see it is, I can draw a position vector to the center of mass and I can feel like the total mass is acting at that particular position. Now we will be taking it for granted that weight will be acting at the center of mass for torque, for force, whatever it is, but we need to understand why we are doing that. So when you do it mathematically, we will be getting that result. After getting the result, we will be understanding the physical meaning and we will be going with the physical meaning. What is the physical meaning? It's like it will behave as if the total mass is acting at the center of mass, even for F equal to ma or torque equal to I alpha. Now similarly, if there is a rigid body and if there is some frame, let me say center of mass frame, center of mass is accelerating this way. So when I observe from center of mass frame, I will be finding pseudo forces on each mass. So if I want to calculate the torque due to those pseudo forces, then what I will be getting? M1 into, this is AC. Okay, minus AC bar. You can take it as minus AC bar. If AC bar is this way, then this will be minus AC bar. So I can do the same thing. It's just like torque due to weight thing. So finally you will be ending up with this one. So the meaning is, you can feel like instead of individual pseudo forces, you can put the entire pseudo force here, which is total mass times total acceleration of center of mass, but in the opposite direction. Acceleration of center of mass is this direction, so pseudo force must be this direction. So that can be the result. Now that is about this particular point. Now what we did, we calculated torque due to pseudo forces in center of mass frame about this point. torque due to pseudo forces in center of mass frame about this point, that turned out to be as if the net weight will act through the center of mass. So that is not going to be 0 in this particular question, but can I change some point? Now what I did, from ground frame I shifted to center of mass frame. From center of mass frame, now I am in center of mass frame. I am observing from center of mass frame. When I am observing from center of mass frame, about this point torque is not going to be 0. About this point torque is not going to be 0, but about this point torque is going to be 0. So torque due to pseudo forces about center of mass point is going to be 0. I mean this, yeah, I think you don't have to take this as AC, you can take it as some random frame, like some random frame which is accelerating. So when you observe from that particular frame, what will happen, pseudo forces will be coming into picture. Those pseudo forces, net will be behaving as if it is passing through center of mass. So when you take torque from center of mass, then torque due to pseudo forces is going to be 0. Now, yeah, this is only like when you are observing from translating an accelerating frame. Okay, so whatever it is, center of mass frame helps because torque due to pseudo forces is going to be 0 in generally for our questions. So there were some other simple examples. It's like there is some rod which is at rest, I mean which is in equilibrium. So that is translational equilibrium and rotational equilibrium. So you need to find the tensions in the strings. So by symmetry you can say both must be equal and T1 equal to T2 equal to mg by 2, which you must be doing from Newton's laws. Now what I am going to do is I am going to make it the other way, that is net torque must be 0. So when I take torque about this particular point, it is L by 2 into mg, that must be equal to torque because of this force which is L into T2, because torque due to T1 will be 0. So from there we will be getting T2 equal to mg by 2. So thereafter I can take torque about this point, torque due to T2 will be 0. Torque due to mg will be L by 2 into mg, torque due to T1 will be T1 into L. So from there you will be getting T1 equal to T2 equal to mg by 2. You can see whether you are correct or not. T1 plus T2 equal to mg. Net force is 0. Now modified, I am putting the string here. Now T1 and T2 won't be equal because it is not symmetrical, it not be equal, where this distance is L by 2. So what I can do, again I can go with the same thing, taking torque about this particular point, L by 2 into mg equal to 3L by 4 into T2. From there I will be getting T2. I will take torque about this point, so mg into L by 4 equal to T1 into 3L by 4. I will be getting T1 is this much. When I add T1 plus T2, I am getting mg. So T1 plus T2 must be equal to mg. Yes, that is right. Now the next question is, there is a rod which is hinged here, and if you leave it, what will happen? It will fall. So what I am doing is I am applying some force so that it is in equilibrium. So what must be that force? What must be that force? Or what? Yes, what must be that force? Now that's the question. So what I can do, it must be in translational equilibrium and rotational equilibrium. Now I can't use net force equal to 0 properly because mg is one force and this is one force. Now apart from that there will be hinge reaction. I don't know hinge reaction will be in which direction. So it can be in some random direction. So what I will be doing, I will be resolving into two perpendicular components. I will be taking one component along x axis, one component along y axis. Just understand, it is x and it is y. This is what I was taking. So if I want to write net force equal to 0 along x axis, this is the only force. So if I make net force along x axis is 0, then this will turn out to be 0. So I can conclude hinge reaction will be only in vertical direction. Now if I want to make net force equal to 0 along vertical direction, this is mg, this is f. So this force must be mg minus f. So summation of these two must be equal to mg. But what I did here, I didn't do anything, like I introduced one more variable unnecessarily, right? So when I make net force equal to 0, I am introducing one variable and I am writing one equation. Now there is no point of writing equation by, most of the times there is no point of writing equation by introducing new variable, right? So what we can do, instead of going by force method, we can go by torque method. When I take torque about this particular point, torque due to this force will be 0. Torque due to mg must be balanced by torque due to f, that is mg into L by 2 equal to f into L, f equal to mg by 2. Now once I get f equal to mg by 2, then what will be this force? This force will be mg minus mg by 2, which is mg by 2. That I can see. If this force is mg by 2, this force is mg by 2, net upward force is mg, net downward force is mg. So it is in translational equilibrium also. So mg by 2. you can see upward force is mg, downward force is mg. Now, yeah, there was some question like there are two equal masses, so what must be this particular angle? And I think, I don't know. Okay, the question goes like there are two masses, two rods of mass m and length L, mass m and length L. So what must be the angle between them, so that if you hang them, one rod will be exactly horizontal. Now I am not going to do it. I mean, it may be little confusing. You can see that I will be going with little simpler example than this. It is like, if there are two rods which are making an angle 90 degrees, when you hang it to the topmost point, what angle this rod will be making with the vertical? That's the question. So for that question, what I will be doing, I will be finding the center of mass of this rod first. Now center of mass of this rod. Now the net center of mass will be lying here. Now this distance is L by 2, this distance is L by 2. So center of mass will be at L by 4, L by 4, L by 4, L by 4. Now I need to find this angle. So if I want to find this angle, this is L by 4, this is 3L by 4. So tan theta equal to L by 4 by 3L by 4, which is 1 by 3. Now if I hang it at this particular point, this particular line will become vertical. Now I am drawing from this figure to this figure. When I hang it to this point, this line which is joining the center of mass will become perpendicular. Vertical. Now what is the reason? The easiest reason I can give is, when it is in equilibrium, net force must be 0, net torque must be 0. We will be hanging on to net torque. If I calculate torque about this particular point, torque due to these forces will be 0, x and y. Let me say some x and y. Forget about these values. I will show you like why they are getting. So torque due to these two forces, hinge reaction will be some random direction. So I don't know. I will be taking it has some x component, some y component. So torque due to hinge reaction will be 0. Now the only other force is weight. Now torque due to weight must also be 0. That's the only way we can get torque is 0. How can that happen? Only when mg is passing through this line. Only if mg passes through this line, then the torque due to weight will be 0. So that is the reason when you hang somebody, then the center of mass will be along the vertical. So I understood that. So this angle what we calculated is tan theta equal to 1 by 3. So that's all. Now my aim is to find what is the hinge reaction also. Now net force along x-axis must be 0. The only force along x-axis is this much, so that has to be 0. Now net force along y-axis must be 0. There is weight 2 mg. So the hinge reaction also must be 2 mg, right? So the entire information, is there. Now if someone don't want to find center of mass and draw the figure later, you have the other method. You can generalize the figure and you can say torque due to this weight must be balanced by torque due to this weight about this particular point. When you do that, you will be getting tan theta equal to 1 by 3. Now the next question is, there is some rod which if you leave it, it will go. So I am trying to push it with some force F here. Now what must be that force? Now this is frictionless, this is also frictionless. To make the question easy, how many forces will be acting on this rod? Mg, and normal from this ground, and I am applying some force F here. Now this is the given structure and it is in equilibrium. Equilibrium represents translational equilibrium as well as rotational equilibrium. Now follow my steps like one by one. There will be many other things in the other figure, so but follow my steps. Now net force must be 0 along any axis. So what we'll be doing, we'll be taking any two mutually perpendicular axes generally. So net force along horizontal axis must be 0. So this is N and this is F. So those two must be equal in magnitude. Now vertically mg and N. So these two must be equal in magnitude. So when I put them, I can say N must be equal to same as F value and this small n must be same as mg value. Now how I got this equal to F, this equal to mg, net force along x-axis is 0, net force along y-axis is 0. Now apart from that, torque must be 0. Now torque must be 0 about which point? Now the thing is, if I will show you later, if net force is 0 and if you can show net torque is 0 about any one point, then net torque will be 0 about any point. That I will be showing later. Anyway, so you can take torque about any point and you have to show it is 0. Now the easy way I can do it is, the easy points are either this point or this point or this point or this point, something like that. So I will be going with torque about this point so that I can avoid torque due to this force and torque due to this force. Now net torque must be 0 about this point, torque due to this one is 0, torque due to this one is 0. So torque due to mg is this perpendicular distance which is L by 2 cos 60 into mg. L by 2 cos 60 into mg, and torque due to this force will be this distance, which is L cos 30 into F, L cos 30 into F. L cos 30 into F will be torque because of this force, is L cos 30 into F. Now torque due to weight is this perpendicular distance, which is L by 2 cos 60 into cos 60 is 1 by 2. Right. So when you do that, you will be getting F equal to mg by 2 root 3. So we got F equal to mg by 2 root 3. So this will be mg by 2 root 3. This will be mg by 2 root 3. mg. So we got every other information. Now if you want, you can put every information in the figure, and you can see like, will the torque become 0 about any other point, okay. Okay, I didn't take torque about this. Okay, I think yes, I have showed you like by taking torque about this point, you can see. Actually, I have taken torque about this point while writing the PDF. The reason is torque due to this force is 0, torque due to this force is 0. Actually, I don't have to, why I am taking this point is so that I don't have to even bother like what is the value of this, what is the value of this. If I take torque about this point, torque due to this unknown normal will be 0, torque due to this unknown normal will be 0. Though it is known here, like I could have avoided like finding what is the value, what is this value. So torque due to this normal will be 0, torque due to this normal will be 0. Now torque due to this mg must be balanced by torque due to this f. Mg will try to rotate it this way, this f will try to rotate it this way. So torque due to this mg must be equal to torque due to this f magnitude wise. Anyway, whatever it is. Now I have written here something like, if the net force is 0 and net torque is 0 about any point P, then the net torque will be 0 about any other point. Now there is some proof for this. Mathematically you can see torque due to forces whose sum is 0. So that is, if summation of forces are 0, there are n forces F1 plus F2 plus F3 plus and so on. If that total sum is 0, then if we calculate torque about any one particular point, then that is position vector of first particle with respect to that point cross force acting on the first particle. Now similarly, all such particles sigma. Now that I can write as position vector of first particle with respect to P can be written as position vector of first particle with respect to O plus position vector of O with respect to P, vector representation, right, vector addition. So when I expand it, I will be getting something here. Now this is looking exactly same as this one. What is the only difference? Instead of P, it is O. So the meaning is, if this is torque of the system about point P, I can say this is the torque of the system about O. But what about this term? This term is ROP. ROP is a constant thing. Position vector of O about P is a constant thing. So I can take it out of that summation. So summation of Fi. Now summation of Fi is 0. Now this is the good thing about, if the forces are, summation of forces is 0. If the summation of forces is 0, then this term is going to be 0. When this term becomes 0, I can show you torque about point P will be same as torque about point O. So if the forces, if there are 10 forces, if the sum of those 10 forces is 0, then the torque because of those 10 forces will be same no matter about which point you will be calculating. So if there are 10 forces and the summation of those 10 forces is 0, then torque due to those 10 forces will be same no matter about which point you will be calculating the torque. Now this is the thing. Now in this particular question, what we did, we understood net force is 0. How many forces are there? There were 4 forces. In the previous question, there were 4 forces, 1, 2, 3, 4. Summation of all these forces is 0. So torque about point P we calculated, that is 0. So when torque about point P is 0, torque about any point must be 0. Because the summation of 4 forces is 0, no matter about which point you will be calculating the torque, that must be same, which is 0 in this particular case because it is in equilibrium. Right? Now we will be using this one at other place also. In magnetism, torque is M bar cross B bar, we will say. Torque is M bar cross B bar, we will be saying. But we never mention like the axis is, what is the axis through which it is passing and stuff. Right? Now torque, now there if you see, that we have defined when you keep a current carrying loop in a uniform magnetic field. And we already know one result, that if you keep some current carrying loop in uniform magnetic field, then the force on it because of those magnetic forces will be 0. So when you keep current carrying loop in uniform magnetic field, then the net force on it will be 0 because of that magnetic forces. Now if the net force is 0, it doesn't matter about which point you are calculating the torque, it will be same. So torque will be M bar cross B bar no matter about which point you will be calculating the torque. So knowingly or unknowingly we will be using it. Now going to something called couple. Couple represents equal and opposite forces. So if there is a rod and if I apply some force F here, some force F here, where this distance is L by 4, L by 2 and stuff. So I want you to find what is the angular acceleration. Now center of mass won't be moving, because the net force is 0, center of mass won't be moving. So what will be the torque about center of mass? F into L by 4 plus F into L by 2. This is the torque about center of mass, that equal to I into alpha. So from there I will be getting alpha value. Now here you can see net force is 0. So maybe by definition wise if I go, I can say like it is in translational equilibrium, maybe, but not in rotational equilibrium. So I can't say this is the equilibrium condition. It is not in equilibrium. Now I have rounded this. Now why I have rounded this is summation of these two forces are 0. If summation of forces are 0, then the torque will be same no matter about which point I will be calculating. So I will calculate torque about this point. If I calculate torque about this point, torque due to this force is 0. Torque due to this force is 3L by 4 into F. So total it will become 3L by 4 into F. This is 3L by 4 into F, right? So if I calculate about center of mass, I am getting 3 by 4 into F into L. If I calculate about this point also, it is getting 3 by 4 into F into L. So that generalized proof we have done already. If the summation of forces are 0, then the torque because of those forces about any point will be same. But if that's the case, then will the angular acceleration come out to be same? We know rigid body's angular acceleration has to be same no matter about which point it has to be. So I will try to get it. So what we are trying to do? We are trying to calculate torque about this point, torque from this point. Torque due to this force is 0, torque due to this force is F into 3L by 4. So summation must be same just earlier. But this is not equal to ml square by 3 into alpha, moment of inertia into alpha. Torque equal to I alpha, but the torque includes pseudo force also. In the earlier case, center of mass was not accelerating, so pseudo force was not there. Even if pseudo force was there, that doesn't matter when we work from center of mass frame, center of mass position, because pseudo force will pass through center of mass position, which we have calculated. So we can use that result, and when we are observing from this frame, we can say, when I observe from this point, we can say pseudo force will pass through center of mass. Actually it will pass through different points. The summation will behave as if it is passing through center of mass. So torque due to this force is 0, torque due to this force is F into 3L by 4, torque due to pseudo force is this much. So torque due to actual forces plus pseudo force must be equal to I alpha. But torque due to pseudo force will become 0 when you observe from center of mass point. So that is one important thing about center of mass point. So it will give answer for every question, but sometimes it may go in a lengthy way, but it will give answer for every question. You won't be making any mistakes, because even if you forget taking pseudo force thing, it will make it 0 when you observe from center of mass point. Okay, anyway, so when I do the manipulation, I will be getting alpha equal to 9F by ml, which is same as what we got earlier. Now, some other question, there is something like, if there is 50, if I apply 50 Newton here and 10 Newton here, where this length is 1 meter, this length is 1 meter, what will be the effective force? So now what does it mean by effective thing? Whenever I say effective, I need to replace all the things with single force such that the motion will be same as this one. Now what does it mean by motion is same as this one? Acceleration must be same, acceleration of center of mass must be same, and angular acceleration also must be same. Now what is the net force in this particular case? It is 25 equal to m into a. What about the torque? Torque about center of mass will be 15 into 1 minus 10 into 1. Now what about these are the torques because of these two forces, but there will be pseudo force also, because I will be observing from this particular point. So but pseudo force, torque due to pseudo force will pass through this point, right? So if pseudo force is passing through this point, then the torque due to pseudo force will be 0. Now that is the good thing about center of mass point. Torque due to pseudo forces will become 0, especially when the frame is accelerating linearly, right? So torque due to 50 Newton, torque due to 10 Newton, torque due to pseudo forces is 0, that equal to IC into alpha. Now A must be same in both the cases and angular acceleration must be same in both the cases. For that, at what distance you need to apply that total force. Now for same acceleration in both the cases, we can clearly see the net force has to be 25. The net force has to be 25 for the acceleration of center of mass to be same. But what about rotation? In order to make the rotation, I need to see at which point I need to apply so that I will be getting the same alpha. So if I apply at a distance x, then the torque will be x into 25. X into 25, that must be equal to I alpha, which is how much? Which is 5 from the first case. So this must be equal to 5. So you will be getting x is 1 by 5. So effectively, what is the thing? If you want to replace these two forces with a single force of 25 Newton, where you need to replace it? You need to replace it at a distance 1 by 5, so that it will be giving the same effect as this case. Now here also pseudo force will be there, torque due to pseudo force will become 0 when we calculate about this particular point. No. Yes, torque, okay, it is just like revisiting, because torque due to pseudo force will become 0 about center of mass point. So that's the thing. Now let me say there is a block on inclined plane which is in equilibrium, Now this length is here, this length is here. Now there will be weight. I have resolved into two components. The angle is 45 degrees to make it easy. Now if it is in equilibrium, if this force is mg by root 2, then the friction has to be mg by root 2, and normal also must be equal to mg by root 2. But if normal is passing through this point, it won't be in equilibrium, because you can see when you take torque about this point, torque due to this component and normal will be 0, but torque due to friction won't be 0. So normal won't be passing through this point. So normal will be passing through some other point, so that it can balance the torque because of this friction. I will be taking torque about this particular point. Torque due to weight is 0. Torque due to friction is trying to rotate it in anti-clockwise direction. So normal will try to rotate it in clockwise direction. For that, normal must come in this position. So I will be assuming some position, and so torque due to friction must be equal to torque due to normal. When I calculate it, I will be getting a by 2 into friction mg by root 2, that must be equal to x times n. So x will turn out to be a by 2. The meaning of a by 2, I have just put this thing in the figure, a by 2 in the sense exactly at the corner, right. So normal is acting here, now it is in equilibrium. Normal won't be acting through the center in this particular case, right. So you have to be careful about that. Now there were some other examples. If I apply 10, okay, so first of all, this length is 4, this length is 2 given. Now it is in equilibrium. If I am applying 10 Newton, then what will happen? There will be 10 Newton friction here. Okay, weight must, it is in equilibrium in vertical direction also, so net force must be 0 along vertical. So if this is 10 Newton, then there must be normal 10 Newton. But why it can't pass through center of mass? You can see when I take torque about this particular point, if at all I assume normal is passing through center of mass, torque due to normal will be 0, torque due to weight is 0, torque due to this force is 0, but torque due to friction is not 0. So from there I can understand that normal is not going to pass through this point, but normal will pass through this region or this region. Now if I take torque over this particular point, torque due to this force is 0, torque due to this force is 0, torque due to friction is clockwise, so torque due to normal must be anti-clockwise, so normal must be somewhere in this region. So if I take this distance as x, and if I calculate torque because of friction must be magnitude wise equal to torque because of normal, I will be getting this value as 1 meter. You can see if I remove this, normal will shift back here and friction will become 0. Right, when I start applying, normal started shifting so that it will stay in equilibrium. So if I apply 10 Newton here, you can prove the same way. Normal will be 10 Newton for vertical equilibrium, but it will shift to a distance 1.5 meter, 1 meter to 1.5. So I am applying the same amount of force, but I am increasing the distance. Now what will happen if I apply here? If I apply here, then still for vertical equilibrium these two must be equal. Now normal shifted to the end, because what is this distance? This is 2. So 10 into 2. Torque because of this one will be 10 into this perpendicular distance, which is 2. That must be equal to 2 into 10, right? Okay, sorry. Now if I take torque over this point, torque because of this one will be coming, torque because of this one will be coming. Now here also you need to take torque because of, in the very first case, torque because of 10 Newton is going to be 0 about center of mass, but in this case torque because of this force is not going to be 0. In this case also torque because of this force is not going to be 0. So when you calculate torque about this point, torque due to these forces will be trying to rotate in clockwise, torque because of normal will try to rotate in anti-clockwise, so you can get the distance as 10, or else you can see when you start shifting 10 Newton upwards, normal started shifting this way so that it can stay in equilibrium. So there will be some limiting case where after this it will topple. So if there was some imaginary height or some massless height, if you push it there, what will happen? It will be toppling. So just before toppling, what will happen? Normal will shift to the extreme corner. So while toppling, we will be taking torque about this particular point, this toppling point, so that we can make things much easier, because it will be rotating about this particular point, right? So we can do questions from center of mass point anytime, but to make sometimes questions easy, we will be shifting on to some points which are stationary, like when some rod is hinged, we will be looking from hinge. When something is toppling about some particular point, we will be looking from that particular point. Okay. So angular momentum of system of particles. And first we defined torque and angular momentum for single particle. Thereafter we went for system of particles. Thereafter we have seen for rigid body. Now we are revisiting it again to look at it like from center of mass frame. So torque of the system equal to torque due to individual particles, just the definition. Now position vector of first particle will be given as position vector of center of mass plus position of that particle, first particle, with respect to center of mass. Velocity of first particle is velocity of center of mass plus velocity of particle with respect to center of mass. Position vector of particle is position vector of center of mass and position vector with respect to center of mass. Velocity of particle is velocity of center of mass and velocity with respect to center of mass. This tilted thing represents velocity with respect to center of mass. So thereafter I will be expanding, I will be getting 4 terms. So I mean there is some math here. So finally you will be ending up with these 4 terms. Now this one I have written like this, so because this equation, the similar term came here, right? This is angular momentum of the system. This is angular momentum of the system with respect to center of mass, tilted one, right? Now what about this? This is as if like the total mass is moving with velocity of center of mass, like position vector of center of mass and velocity of center of mass and total mass. It is as if you are looking at only center of mass. If you are concentrating only on center of mass, if you are looking like there is some point, if you assume like the total mass is concentrated at center of mass and it is moving with velocity of center of mass, then the momentum, angular momentum will be this much. Now this term I am going to show 0, this term I am going to show 0. So what is this term? m1 v1, m2 v2, m3 v3. So which is total mass into velocity of center of mass in which frame? In center of mass frame, which is going to be 0. Velocity of center of mass in center of mass frame is 0. Now what about this one? m1 r1 plus m2 r2 plus m3 r3, which is m into position vector of center of mass in center of mass frame, which is going to be 0. So these 2 terms will turn out to be 0. So angular momentum of the system is turning out to be angular momentum of center of mass and angular momentum about center of mass. In case of rigid body, this will be like normal only. You will be calculating it. This will turn out to be IC into omega for a rigid body. But this is valid for any point masses, but just for rigid body, this will turn out to be IC into omega. Now similarly, we will be looking at kinetic energy term in the same way. Kinetic energy of system equal to kinetic energy of summation of individual particles. So velocity of first particle is velocity of center of mass plus velocity with respect to center of mass. So when I expand it, I will be getting 3 terms. Now this term looks exactly same like initial term. The only difference is this is kinetic energy with respect to ground. This is kinetic energy with respect to center of mass frame. So kinetic energy with respect to center of mass frame. Now this is as if the single particle, the center of mass is moving with some particular, as if the total mass is concentrated at the center of mass. And this term I can show it as 0 because sigma m1, sigma mi vi, which is m1 v1 plus m2 v2 plus m3 v3, that is total mass into velocity of center of mass in center of mass frame, which is going to be 0. So finally you will be ending up with kinetic energy equal to kinetic energy of center of mass and kinetic energy with respect to center of mass. This is valid for any system, but for rigid body it will turn out to be half IC into omega square. Now you have seen the same thing in center of mass. In center of mass, if there are 2 particles moving, then this term will turn out to be half into mu into v relative square. Now, okay, there is a question we are just going to use that whatever we got, angular momentum of system equal to angular momentum of center of mass and angular momentum about center of mass. kinetic energy equal to kinetic energy from ground frame equal to kinetic energy of center of mass and kinetic energy about center of mass. Now we will be seeing the same thing. Now I will be calculating angular momentum about O. Angular momentum about O will be same as angular momentum of C about O plus angular momentum of rod about center of mass, right? So angular momentum of center of mass about O, how I can calculate it? As if the total mass is moving with velocity of center of mass. What is the velocity of center of mass? L by 2 omega. So if there is entire mass concentrating here, then what is the angular momentum? L by 2 into m into v, which is okay, L by 2 into m into vc, L by 2 into m into vc. How this came? As if the total mass is concentrated here and its velocity is velocity of center of mass. So L by 2 into m into v, that is the angular momentum of center of mass. Now what about angular momentum about center of mass? Angular momentum about center of mass is IC into omega. Both are in the same direction. L by 2 into m into vc into the board, IC into omega again into the board. So what is Vc? Vc is L by 2 into omega. When I substitute it, when I modify it, I will be getting ml square by 3 into omega, which we already know because we have done some proof and we have cross checked it. It is moment of inertia about this axis into omega, which is ml square by 3 into omega. So whether you directly write ml square by 3 into omega or you write it like angular momentum of center of mass and angular momentum about center of mass, you will be getting the same result. You don't have to bother about that. Okay. Now kinetic energy of center of mass is half m into vc square. About center of mass is half IC into omega square. When you add this, you will be getting half into ml square by 3 into omega square, which is expected because when something is rotating about some particular axis, then kinetic energy will be half into I about that particular axis into omega square, which we have seen already. Yeah, right. Angular momentum is I into omega, kinetic energy is half into I into omega square. This is like revisited thing. I just pasted it again so that I can show you. Yeah, this is the results we got. Again, we got it by the other way. What is the other way? By looking at it like motion of center of mass and motion about center of mass. Now that is the reason we will be looking from center of mass frame, because center of mass will make the things easy for understanding, and at the same time you can see angular momentum calculation is going to be easy, kinetic energy calculation is going to be easy. It is looking as if all the equations look as if you can visualize the motion like motion of center of mass and motion about center of mass. Angular momentum equal to angular momentum of center of mass and angular momentum about center of mass. Kinetic energy equal to kinetic energy of center of mass and kinetic energy about center of mass. So you can see any particle's motion as motion of center of mass and motion about center of mass, because you can write the equations much simpler. Actually you can see motion of any particle, let me say motion of particle q I want to see. I can see it like motion of particle p plus motion of particle q with respect to p. But writing equation is going to be difficult if I choose p. But what is that point which makes me write equations easily? That is center of mass. So I will be seeing from now onwards, I will be seeing any random motion as motion of center of mass and motion about center of mass. Now there is next question. There is a rod which is hinged here, which is vertically like this. I am slightly pushing it so that it will be rotating. Now when it has fallen some particular distance, when it became horizontal, it would have gained some angular velocity, it will be having some angular acceleration. Or I can say center of mass is performing circle of radius L by 2. So at this particular moment, if the angular acceleration is alpha, then the center of mass acceleration will be L by 2 alpha, and if it is rotating with omega, center of mass acceleration will be ml square by 2, omega square L by 2 towards center. This is centripetal, this is tangential, right? Now if I look at the forces, what all forces are acting? There will be weight and there will be hinge reaction. Hinge reaction direction I don't know, so I will be taking it as x and y. So these are the things. Now I will be finding omega. How to find omega? I will be using conservation of energy from this to this. Potential energy is getting converted into kinetic energy. Potential energy mgl by 2 is getting converted into half into I about this axis into omega square. That is first equation. Now second equation, torque equal to I alpha. If I will be taking torque about this point because I don't have to bother about pseudo forces and stuff. It is much simpler because it is not accelerating, and at the same time I can make torque because of these two forces 0. So if I take torque about this particular point, there will be torque because of only mg, so which is L by 2 into mg equal to I alpha. Now other equation what? Okay, from here I got omega, I can get omega from here. By conservation of energy, I can get omega. By torque equal to I alpha, I can get alpha value. So from here, I know what is the omega value. From here, I know what is the alpha value. Now, if someone asks me to find the Hinge reaction, what I can do is, now it is a rigid body. When it is a rigid body, I will be looking at center of mass. Center of mass has some acceleration along this direction. So there must be some force which must be providing it. Who can provide that? Only this force. So x equal to m into omega square L by 2. Now vertically it is having acceleration L by 2 alpha. So who will be giving that? Net force mg minus y equal to total mass into acceleration L by 2 alpha. So from here I will be getting the value of x. From here I will be getting the value of y. So what are the step by step? Actual question is to find the Hinge reaction. So what are the step by step things we did? We found omega, we found alpha. Thereafter we wrote F equal to ma along two mutually perpendicular axes. And we can take the resultant of x and y to get the answer. So x is 3 mg by 2, y is mg by 4. Right. Now the same question I am trying to solve from like center of mass frame. Previously I did from Hinge frame, it turned out to be much simpler. In center of mass frame, this is going to be difficult, but it will give us the answer. Now follow the step by step things what I will be saying. Now it has fallen down. When it has fallen down, center of mass will be having some velocity, I don't know how much it is. Center of mass will be having some acceleration, I don't know how much it is. So velocity of center of mass will be vertically downwards. So acceleration of center of mass ay and ax, which we can predict because of the motion of center of mass. Now these are the forces, right? Now till here it is okay. Now what I will be looking at, I will be looking at the motion like motion of center of mass and motion about center of mass. Whatever is represented in blue color, that is motion of center of mass. Center of mass is having velocity v, vertical acceleration ay and horizontal acceleration ax. Okay. Now that is motion of center of mass. So if I want to look at this particular point, I can look at this particular point's motion as motion of center of mass and motion about center of mass. Now what I will be getting if I take motion of center of mass, I will be getting all the blue color things. Motion of center of mass is acceleration is ay, acceleration is ax and velocity is v. These blue color terms will be coming because I am seeing it like motion of center of mass. And apart from that, I need to see the inclusion of motion about center of mass. About center of mass, this entire thing is rotating. So it will be having a velocity L by 2 omega. It is rotating with omega, right? So it will have velocity L by 2 omega. Apart from that, angular acceleration is alpha. So it will have acceleration L by 2 alpha. Now it is rotating, right? So there must be some centripetal acceleration also. Okay, there must be some centripetal acceleration also, right? So omega square L by 2. So these blue color terms came because of motion of center of mass. These green color terms came because of motion about center of mass. Now what we know about this point, that point actually is not moving. So the meaning is its velocity must be 0, its acceleration must be 0. So if the velocity has to be 0, then I can say v must be equal to L by 2 omega. So v equal to L by 2 omega because that point is not moving. Now vertical acceleration also must be 0. So ay equal to L by 2 alpha. Similarly, horizontal acceleration also must be 0. So ax equal to omega square L by 2. So I will be getting these three equations by constraint relation. So I will be looking at the motion like motion of center of mass and motion about center of mass. But there will be some point whose motion we already know. That is this point. We know this motion. It is not moving. So that is the constraint. So we are getting some values using the constraint. Now apart from that, now again I will be going back to normal thing. I will be writing force equation for center of mass. So mg minus y equal to total mass into acceleration of center of mass along this direction. So Hinge reaction equal to, x equal to total mass into acceleration of center of mass along this direction. These are F equal to ma equations. Similarly, I will be writing torque equal to I alpha. If I write torque equal to I alpha about center of mass, torque due to weight is 0, torque due to x is also 0 because that will be passing through this point. So there will be torque because of only y. So y into L by 2 equal to ml square by 2 into alpha. This is torque about center of mass. And center of mass is accelerating. So torque due to pseudo force also we need to take, but torque due to pseudo force is going to be 0, it will be passing through center of mass there. So that's the good thing about center of mass. Though in this particular question it is going to be lengthy, but see I didn't even think of pseudo force, I just wrote the equation, but even if you think of pseudo force, still you will be getting the same equation. So even if I forget it, center of mass will correct it, right? So this is energy conservation. Again, energy conservation, how I have seen, drop in potential energy will be converting as kinetic energy. Kinetic energy is kinetic energy of center of mass and kinetic energy about center of mass. So basically these are the equations I need to write. I need to write 7 equations if I try to solve this question from center of mass frame. After that it's about solving the equations. So I need to write 7 equations if I do from center of mass frame. But the same question when I did from this frame, this hinge frame, then I need to write only 4 equations. So that is the reason, though we can solve all the questions from center of mass frame, sometimes we don't do it from center of mass frame because the number of equations will become less from some certain frames. But if you are hopeless, center of mass frame will always help. Center of mass frame, especially if you observe from that particular position of center of mass. Right. So, and if there is some rod which is rotating about this point, yeah, you can assume like there is some massless thing here, whatever it is. So if this velocity is large, this is less, that you can see like when it is rotating about this particular point, you can see the near point, the near masses will be having less velocity, the farther masses will be having more velocity. By that logic, if there is some rod whose points, this point velocity is v2, this point velocity is v1, u1, u2, you can see I have put the sizes depending on the magnitudes. So from there you can understand there will be some point by continuity. It is reducing in this direction, thereafter it is increasing in this direction. By continuity you can see there will be some point which is at rest. So here you can feel this entire thing is rotating about this particular point. Here you can feel the entire thing is rotating about this particular point. That particular point, I mean in this case rotation is about this axis. That particular axis is called as instantaneous axis of rotation, right? Now how to find instantaneous axis of rotation? If you know any two particles velocities, what you will be doing? You can see about instantaneous axis, you can feel like all the velocities will be perpendicular to the line joining, right? So if there is axis, so all the velocities will be perpendicular to this line, right? So what you can do, if you know velocity, drop a perpendicular for that. You know this velocity direction, so drop a perpendicular. You know this velocity direction, so draw a perpendicular. So wherever they will be meeting, that will be instantaneous axis, because from instantaneous axis, all the points must be moving in circular motion, that is their velocities must be perpendicular. All the points must be moving in circular motion at that particular instant, so velocities must be perpendicular to the line joining. So now this is the instantaneous axis. From instantaneous axis, no matter which point you will be looking onto, if you look at this point, that will be having velocity perpendicular to the line joining. If you look at this point, that will be having velocity perpendicular to the line joining. So no matter which point you will be taking, that velocity will be perpendicular to the line joining. Now that's about instantaneous axis. Instantaneous axis represents some axis which is at velocity is 0, acceleration need not be. So where we will be feeling the entire thing is rotating about that particular axis. So if there are two such axes and the common point we call it as instantaneous center of rotation and stuff. Anyway, so if this end is moving with velocity 10, this end is moving with velocity 5, where the instantaneous axis will be located? You can see like this is 10 in this direction, this is 5 in this direction. So it must be reducing and it must become 0 somewhere, and it must increase in this direction and it must become 5. So let me take the distance as x. So I am assuming this is instantaneous axis of rotation, which is at rest, right? So L into omega will be, if this is at rest, you can see this is like one rod whose length is 2 minus x. You can see this rod has length x. So what will be this velocity if it is rotating to omega? X into omega. So x into omega must be equal to 5. Or I can say this is 2 minus x. 2 minus x. 2 minus x into omega must be 10. B equal to r omega. So x into omega must be equal to 5, or 2 minus x into omega equal to 10. Or I can say omega is 5 by x or 10 by 2 minus x. When I solve for that, I will be getting x equal to 2 by 3. So instantaneous axis of rotation will be located at a distance 2 by 3 from here or 4 by 3 from here, right? Now if there are walls like this wall, and there is a rod placed here where this angle is 37 degrees. And if they say if this end is moving with speed 3, then what will be the angular velocity? Then how you will be doing it? You can you know this velocity direction is horizontal, this velocity direction is vertical. So you will be dropping some perpendicular line for this velocity. You will be dropping some perpendicular line for this velocity. It looks like this. So wherever they will be meeting, that will be the instantaneous axis. So you know this velocity is going this direction. So what will be the angular velocity of this particular point? It will be V equal to R omega. So 3 equal to 3 times of omega. So omega will be 1. Omega will be 1. So you can visualize like there is some kind of massless rod joined right now. So there is some kind of massless rod joined right now. So the entire structure is moving about this one. Now once I know angular velocity is 1, I can easily show you this velocity is 4 because this distance is 4. R omega is 1. So this velocity will be 4. So what is the other way generally people will be doing it? It's this. You will be assuming this velocity is y, you will be resolving along the rod and perpendicular to the rod. This velocity is 3, so you will be resolving along the rod and perpendicular to the rod. Along the rod velocity must be same because it is rigid body, it can't compress. So y into 3 by 5 equal to 12 by 5. Now apart from that, for calculating angular velocity, you will observe from this particular point. So when you observe from one particular point and when you observe the other one, so relative velocity will become how much? These two, it will become 0. Anyway, that doesn't matter. So you need velocity perpendicular to the line, which is 9 by 5, and this 4y by 5 will be coming again in this direction. When I observe from this particular point, I will be feeling extra velocity how much? 4y by 5. So this particular point will be having velocity 9 by 5 plus 4y by 5 when I observe from this point. So angular velocity will be that particular velocity by that distance. This is 3, this is 4, so this will be 5. So omega equal to 9 by 5 plus 4y by 5 by 5. So one is along the rod, one is angular velocity equation. Find y from here, substitute here, you will be getting omega. You must be getting the same result, you can see. Now there is this question. So in this question, suppose the velocity of this particular point is v. Yeah, there are, okay, you can read the question. It says a sphere is rolling without slipping on 2 horizontal and parallel rails. Those are represented using dots here. So those are horizontal and parallel rails which are going into the plane, you can see. Distance between the rails is equal to the radius of the sphere. If the speed of the center of the sphere is v, find the greatest speed on the point. So that's the question. So basically these two are rails which are going into the board, and you can visualize like the sphere is also going into the board. The sphere is also going into the board. But see, it is pure rolling. So the meaning is the point of contact here will have 0 speed. The point of contact here will have 0 speed. So there are 2 point of contacts. There are 2 points on the body which are at rest. So both must behave like instantaneous. Both must be lying on instantaneous axis, right? So what does it mean by instantaneous axis? Like we will be feeling every other particle is performing circular motion about that particular axis, right? So if there are 2 points whose speed is 0, then those 2 points must lie on instantaneous axis. Now how can that happen? The only way it can happen is when the instantaneous axis passes through those 2 particular points. So from here what we concluded, we understood 2 points are at rest, so we joined those 2 points and we can clearly say that will be instantaneous axis. So every other point will be just rotating about this axis. So about this axis, this particular point will be performing circular motion. Now every other particle will be performing circular motion about this axis. So what is this distance? Now they have given some information. This is equal to radius. So this is 60 degrees, this is 60 degrees, this is 60 degrees. So this length is root 3 by 2a. So if this length is root 3 by 2a, and if it is rotating with omega about this axis, then what will be its velocity? Its velocity will be root 3 by 2a into omega into the board. But what they are asking, they said that is v. But they are asking what can be the maximum speed of some point. That is, the more perpendicular distance it is, the more speed it is, right? So which point has more perpendicular distance? This one. So what is that distance? That is r plus root 3 r by 2. So what is that speed? It is r plus r root 3 by 2 into omega. So for center it is root 3 by 2 into r into omega is v, but they are asking what is the maximum speed, that is r plus r root 3 by 2 into omega. From here you can find omega and you can substitute, you can get the required result. So when there are 2 points at rest, just join them, that is going to be instantaneous axis. Now the question is, okay, I think theory wise I think things are done. These are just some random stuff. So if there is a fixed inclined plane and there is friction here, so there is some circular object which is rolling without slipping, so you need to find, yeah, the question goes like, if there is an inclined plane and if you keep many circular objects and if you leave them from that particular position, and if the friction is sufficient for pure rolling, which object will reach the ground first? So that is, if you take ring, disc, sphere, whatever circular objects you have, and if you keep them, all of them in line, and if you leave them, assuming that pure rolling is happening, so which one will be reaching the ground first? So for that, all we need to do is to see whose acceleration will be more. So basically we are converting that question to see whose acceleration will be more. So the regular traditional method is, obviously weight will be there, weight's component mg sin theta, mg cos theta, so normal will be there, and normal you can say equal to mg cos theta because center of mass is not moving along this direction. Now apart from that, now friction will be there in this direction. Now if someone find difficulty with the direction of friction, just assume friction is not there. If friction is not there, what will happen? Due to mg sin theta, it will try to go this way. So when it is trying to go this way, this bottommost point is trying to go in the downward direction, so friction will try to appear in the upward direction. So now write F equal to ma. When you write F equal to ma along this direction, you can say normal equal to mg cos theta, but that doesn't matter for me, I am not going to write it. So along this direction, mg sin theta minus F equal to m into a, that is acceleration of center of mass. Now similarly, I will be writing torque equal to I alpha about center of mass. Now torque due to weight will be 0, torque due to normal is 0, torque due to friction is F into R, R into F, that equal to I alpha. Now I am taking it as beta mr square, that beta varies for different bodies, so that I can substitute it later. So I equal torque equal to I alpha, but how many unknowns are there? Here F and A, here F and alpha, so we have 3 unknowns. We need one more equation apart from these 2. What is that equation? That is going to be constant. What is the constant? It is pure rolling. The meaning is this bottommost point velocity will always be same as inclined velocity, which is 0. So how that can happen? When that point is not accelerating here, right? So the particular point acceleration must be 0. Now due to translation, we understood the particular point will have acceleration a in this direction. Due to rotation, that particular point will have r alpha in this direction. So a must be equal to r alpha, so that that particular point acceleration will be 0 along the incline. That is, this is no slipping condition. Now there are 3 equations, 3 unknowns, you can solve them. What I did here is, I cancelled r, and r alpha I have written it as a, so I wrote 2 equations, mg sin theta minus f equal to ma, f equal to beta ma, and I added them. I will be getting acceleration is g sin theta by 1 plus beta. Now the good thing to notice here is, it doesn't depend on the mass of the object, it doesn't depend on the radius of the object. The only sufficient condition needed is, it must be pure rolling, that's all. So no matter what it is. So if I take about maybe ring and or solid cylinder and hollow cylinder, for hollow cylinder moment of inertia is, beta value will be 1, for solid cylinder it is half. So which one will reach ground first? If beta value is less, acceleration will be more. So whose beta value will be less, then its acceleration will be more, it will be reaching the ground first. So if you leave solid cylinder and hollow cylinder, solid cylinder will be reaching the ground first, no matter what are the sizes, because it depends only on the beta value. Beta value represents, when we have decided hollow cylinder and solid cylinder, we decided beta values. Now it doesn't depend on what is the shape, what is the size. It doesn't depend on what is the size, what is the mass, what is the material. All it needs is friction is sufficient for pure rolling. So then no matter which solid cylinder you will be taking, it will always win over any hollow cylinder you will be taking, right? Now I can solve the same question in the other way. What I did here is, I know it is pure rolling, so I can take torque about the bottommost point. So bottommost point will actually have omega acceleration this way, but torque due to that pseudo force will be again passing through that particular point. So torque due to pseudo force will become 0. So I can take torque about this particular point. When I take torque about this particular point, friction will be 0, normal will be 0, torque due to this one will be 0. torque due to mg sin theta only will be there. So which will be r into mg sin theta, that equal to moment of inertia about this axis. I can apply parallel axis theorem. Moment of inertia about this axis is beta mr square. So about this axis it will be beta mr square plus mr square, which is 1 plus beta into mr square. I alpha, torque equal to I alpha about bottommost point, which will give me the same acceleration. Here I got it in one step or maybe two steps, for which I have written 3 equations in the first place and I solved it. But that's the traditional method. If you don't know how to do, this one will work in every question. This one will work in every question and you won't make any mistakes while doing this method. But if you want to get little quickly the answers, maybe you can follow some other methods. But if you are getting confused, just stick to this method. Write torque, write F equal to ma for center of mass, write torque equal to I alpha about center of mass, and see the constant relation. That will work for every question. Now I have done the other way also. It is like, if I have left it here, some object has moved by distance L. So then I am going to see, like, now it is pure rolling. So friction is not going to do any work because the bottommost point velocity is always 0. So friction is not going to do any work. So mechanical energy conservation will be valid. So whatever potential energy was dropping, that is this much, is getting converted as kinetic energy. Now kinetic energy of center of mass and about center of mass. Kinetic energy of center of mass, kinetic energy about center of mass, but V equal to R omega. So I can write it like total energy is half into 1 plus beta into mv square. So this is the total kinetic energy which came from looking, I mean the equation came easily because we have already done the derivation. Like it looks like kinetic energy of center of mass and kinetic energy about center of mass. So this is the thing. Now when I differentiate it, I will be getting acceleration is g sin theta by 1 plus beta. Right. So there is no single method, whichever is comfortable for you. Right. So the next question goes like, there is a rod of mass 2m and there is a point mass m which is moving with the speed u, and everything is in horizontal plane. Everything is in horizontal plane. Now it is elastic collision. Elastic collision. Now after hitting, with what velocity rod will move, with what velocity this will move, with what angular velocity it will move. This is the question. So what I will be doing is, after hitting I can see rod must move in the forward direction because the force on the rod is exerted in this direction, so it will go in this direction. Apart from that, the force is exerted in this direction, so rod will try to rotate also. So I am assuming velocity of the rod is v and angular velocity of the rod is omega. This is the first thing I assumed. I assumed velocity of the rod is v and angular velocity of the rod is omega. So if I want to look at velocity of this point, I can see it like motion of center of mass and motion about center of mass. So this particular point will have a velocity v plus L by 2 omega. So, and I know in elastic collision, velocity of approach equal to velocity of separation. What is the velocity of approach? U for this particular point, like along the line joining, along the normal, right? So velocity of approach is u, so velocity of separation also must be u. For that, this velocity has to be v plus L by 2 omega minus u. So what I did, I assumed v and omega. Thereafter I can see what is the velocity of this point. If I know what is the velocity of this point, I can predict what is the velocity of this point. That must be, the difference must be u. Velocity of approach is u, velocity of separation is u, right? Now what I can do, all the forces are internal forces, so I can conserve momentum. All the forces are internal forces, so torque will also be 0, so I can conserve angular momentum also. So I will be conserving momentum of the system, which is m into u equal to final momentum, which is m into its total velocity plus 2m into its velocity. So when I conserve momentum, initial momentum is m into u plus 0 equal to final momentum plus this momentum. So from there I will be getting one relation, but how many unknowns are there? V and omega. So but I need to get one more equation. I have two unknowns, I assumed v and omega, and I try to reduce as number of equations. I applied elastic collision or E equal to 1 in the figure itself, so that I can reduce the number of equations. So there are two variables, v and omega. I have written one equation which is conservation of momentum. The other equation is going to be conservation of angular momentum. Actually we have used conservation of energy also, but how we have used conservation of energy is same as applying E equal to 1, which is same as velocity of approach equal to velocity of separation. So we have used energy conservation while drawing this figure. We have used momentum conservation here. Now we need to do angular momentum conservation. Now angular momentum conservation, will it be valid about any point? Yes, no matter about which point you will be taking, the only forces are internal forces, so torque due to internal forces will be 0, so angular momentum must be conserved about any point. but which points will be good for us? I will show you this point is going to be good for me. So if I talk about this point, now I said all the forces are internal forces, so torque due to internal forces is 0, so angular momentum must be conserved. Now what about which point? So if I take about this point, what is the initial angular momentum of this particle? It is 0. For rod we will be dividing into two parts. Which one is angular momentum of center of mass, one is angular momentum about center of mass. Angular momentum of center of mass is 0, about center of mass is also 0. So initial angular momentum is going to be 0 about this particular point. Even final angular momentum of this point is going to be 0 about this particular point. But angular momentum of center of mass, now I need to find for rod. For rod I will be having two components, one is off center of mass, one is about center of mass. For off center of mass, what I need to do, I need to join position vector and I need to do something, but instead of that what I can do, I can find what is the perpendicular distance. Perpendicular distance is r into m into v, r into, which is L by 2 into total mass is 2m into v. That is in this direction which I am taking positive. Now and plus about center of mass, angular momentum about center of mass is IC into omega, which is in this direction, which is going to be negative for me. M L square by 12, that is moment of inertia into omega. So this is angular momentum of center of mass, which is L by 2 into 2m into v, and angular momentum of about center of mass ml square by 12 into v, both are in the opposite direction. So this one. So you can see clearly that is a simple equation. So v equal to L omega by 6. Now once you get v, we already know this from momentum conservation. We got this one by angular momentum conservation. You can substitute it back and you can get the results. Now you can see conservation of angular momentum equation includes only two terms here basically, but I will show conservation of angular momentum from other point. It involves more number of terms than this. Now we will go for that. I will try to conserve angular momentum about point Q. So what is the initial angular momentum of the system? It is L by 2 times mu, L by 2 times mu, and I have taken this direction as positive now. That is for point mass. For rod, off center of mass is 0, about center of mass is also 0. Now finally for this point mass, it is L by 2 into m into its velocity, angular momentum, perpendicular distance into m into its velocity. Now for rod, there will be two components, off center of mass and about center of mass. Now off center of mass term is going to be 0 because its velocity is passing through this point. Now about center of mass, it is 2m into L square I into omega, 2m into L square by 12 into omega, right? So initial angular momentum equal to final angular momentum. You can see it is little lengthier than earlier conservation of angular momentum, but when you solve you will be getting one more equation. So this equation we got from conservation of momentum, this equation we got from conservation of angular momentum. When you solve them, you will be getting the same result as what we got earlier. Now I can conserve angular momentum about point r also. This will involve one more term extra. Initial angular momentum of point mass, initial angular momentum of rod, both terms are 0. Final angular momentum of point mass plus final angular momentum of the rod, which involves two terms, off center of mass and about center of mass. That's little in the equation, but you will be getting some final term, final equation. This is conservation of momentum, this is conservation of angular momentum. When you solve them, you will be getting required same answer, right? Now the other question was like, if there is a circular object, what you are doing is you are not giving any angular velocity, you are just giving velocity to it. There is friction here. So what will happen? If friction is not there, it will be going this way, the bottommost point will try to go this way. But so if friction comes into picture, it will try to oppose the relative motion, so friction will try to act in this direction. So what will happen if friction acts in this direction? It will try to reduce this velocity, at the same time it will try to create some angular velocity in this direction. So this is at some random moment. At some random moment, its speed would have been reduced and its angular velocity should have been increased. Now when I look at the forces, how many forces are acting on this? Weight, normal and friction. Now in this particular question, weight and normal must be equal because center of mass is not moving in vertical direction. So net force must be 0. So, okay. So if I talk about this particular point, no matter, okay, about any point, if you calculate the torque because of weight and normal, it will turn out to be 0 because they are behaving like action and reaction kind of forces. So if I calculate torque about this point, torque due to mg and torque due to normal will be getting cancelled. So torque due to mg and torque due to normal in this particular question is going to get cancelled no matter about which point you are calculating. But torque due to friction is going to be 0 only about the points on the ground. Torque due to friction is not going to be 0 about some other point. So if I talk about this particular point, torque due to mg and normal summation will be 0, but torque due to friction is not going to be 0. So torque due to friction is going to be 0 about this particular point. So what I can do, I can conserve angular momentum about this particular point. So torque because of mg and normal is combination is 0, torque because of friction is 0. So if torque is 0, angular momentum over this particular point must be same at any moment. So now the question is, if I leave it this way, if I give some velocity and if I leave it, what will happen? Initially u is there, omega, r omega is 0. This bottommost point will have velocity u and r omega, right? U and r omega. Initially u is more, but r omega is less. Initially u is more, r omega is less, right? So what will happen because of friction? This u will reduce, this r omega will increase. At certain moment u will become equal to r omega. At certain moment v will become equal to r omega, that is pure rolling case. Then what will happen? Friction will disappear because there is no relative motion. If there is no relative motion, there is no need of friction. So friction will disappear. After this, friction will disappear and it will keep going with the same motion. So actually the question will be, sorry for not saying the question in the beginning. So the question will be, find the final velocity. Find the final velocity. If you have given initial velocity u, what will be the final velocity? If the moment of inertia is beta mr square. So for that, what we can do, you can find acceleration, angular acceleration and stuff, and you can see v equal to r omega, or you can use conservation of angular momentum also. I am going with conservation of angular momentum. So I can say angular momentum must be conserved about this point. So initial angular momentum of the body will be having two components, angular momentum of center of mass, that is r into mu, plus angular momentum about center of mass, omega is 0, so it is 0. So finally angular, okay, I will be talking about this one also. So what will be the angular momentum at this particular moment? It is angular momentum of center of mass, which is r into m into u dash, plus angular momentum about center of mass, which is beta mr square into omega dash. Both are in the same direction. R into mv and I omega both are in the same direction. Now about for final point, it is again r into m into v plus beta mr square into omega. Now I will be doing something to it. It is pure rolling, right? So v equal to r omega I can write. When I write v equal to r omega, it will turn out to be 1 plus beta into mr square into omega form. So when I calculate angular momentum over this point, the equation is looking like moment of inertia about this point into omega. That is as if it is just rotating about this fixed point. When something is rotating about a fixed point, then we will get angular momentum equal to I into omega, right? So we are getting the equation as if it is rotating about this fixed point. Now similarly, yeah, when I solve it, when I equate this to this, I will be getting the final velocity. Anyway, now if I calculate kinetic energy in pure rolling case, then what will happen? Kinetic energy of center of mass and kinetic energy about center of mass. Again, when I use v equal to r omega, it will turn out to be half into 1 plus beta mr square into omega square. So what is this? This is moment of inertia about the bottommost point, right? So again, kinetic energy equation is looking as if it is just rotating about this point. If it is just rotating about this point, then kinetic energy will be half into moment of inertia about that axis into omega square. That's the same thing we got. So angular momentum equation, we got I about this axis into omega. Kinetic energy equation, we got half into I about this axis into omega square. So we can see that is kind of instantaneous axis of rotation. We are feeling like the entire body is rotating about that point. You can see angular momentum term, you can see kinetic energy term. We are getting as if it is rotating about that particular point, like instantaneous axis. Now in this particular question, till pure rolling happens, friction will be trying its best to avoid relative motion. So friction will be maximum till it comes to pure rolling, that is mu mg. Right, okay. Now there is some other question. Now there is a rod. Now I am rotating with omega. Now given mass of the rod is m, length of the rod is some small l, and acceleration due to gravity are given. So mass, length and acceleration due to gravity are given, and omega is also given. So you need to find, if I start rotating that rod about this axis, so what angle it will be making and what will be the hinge reaction. Now there is no single way to do it. Now I have done in only one method for now, so you can just stick to it for now. Maybe you can find the other ones later. So what I will be doing is, I will be first seeing torque about this point. Now when I take torque about this point, torque due to hinge reactions will be 0, torque due to weight will be there, torque due to weight will be there. So it must be changing the angular momentum, but I can see like the rod is not going to fall down. But if there is torque and rod is not going to fall down, how is angular momentum getting changed? So for that I am seeing what is the angular momentum in the first place. So when the rod is in this position, if I want to calculate the angular momentum of this rod, what I will be doing, I will be taking angular momentum of some particular point, which is r into m into v, r into m into v. So that is the angular momentum of this particular point whose velocity is into the board right now. So angular momentum will be in which direction? R bar cross mv bar. R bar is this way, mv bar is this way. So R bar cross mv bar, which must be this direction, which is perpendicular to x. So angular momentum is in this direction for this particular point. For any point it will be in the same direction. So when you add them, you can add them like scalars. When you do that integration, it will turn out to be this much. So angular momentum of this rod right now is going to be this much, ml square by m omega l square by 3 sin theta in this direction, So what will happen when the rod is rotating? Now rod is this direction. When the rod is this direction, angular momentum is in this direction. So when the rod rotates like a cone, what will happen? Angular momentum also will rotate like a cone. Angular momentum will rotate like a cone, right? So when rod is rotating like a cone, angular momentum also will rotate like a cone. So if angular momentum is rotating like a cone, so let me say it will have some horizontal component. If this is theta, then this will be 90 minus theta, this will be theta. So horizontal component will be L cos theta, vertical component will be L sin theta. L cos theta, L sin theta. So if this is angular momentum, I will be resolving it into L cos theta and L sin theta. So when it is performing a cone, this L cos theta is making circular motion kind of. So it is changing its direction. Magnitude wise it will be remaining same. So it is changing its direction. What about this angular momentum component? This is remaining constant. So out of this angular momentum, if I take it into two components, vertical and horizontal, vertical is not going to change, horizontal is going to change. Not magnitude wise, direction wise. So if angular momentum has to change either in magnitude wise or in direction wise, there must be some torque. Now we will see why the angular momentum is rotating in, changing its direction. Now what I did, I resolved the angular momentum into two components, vertical and horizontal. Now I am not going to bother about this component, or anyway, so angular momentum is in this direction. So when I calculated the torque, in which direction it came? It is r bar cross mg bar. So torque is in this direction. Torque is in this direction. Torque is into the board. Angular momentum is this direction. You can see angular momentum and torque are perpendicular. What will happen when angular momentum and torque are perpendicular? It's like what will happen when velocity and acceleration are perpendicular. Velocity will be changing its direction, right? Like circular motion. The same thing will be happening here. So I'm going to show you. Horizontal component will be this much, vertical component will be that much. It is not going to change. Horizontal component is going to change. So in circular motion you must have seen, right? If radius is rotating with omega, then what will be the velocity of the point, or at what rate the position vector is changing? R omega, right? If radius r is rotating with omega, at what rate the position vector will be changing? R omega. So similarly, if this vector is rotating with omega, then at what rate it will be changing? Omega times its value. So omega times its value. Now how you are getting this? Angular momentum is changing. It can't change by itself, right? Someone must provide that required torque. Who is going to provide that required torque? Torque due to weight, L by 2 into mg sin theta. So from here you will be getting theta value. You will be getting theta value. Once you get theta value, if you want to find hinge reaction, there is only one better way, that is center of mass. So center of mass is not moving vertically, so Ny must be equal to mg. Center of mass is performing circular motion, so Nx must provide the required centripetal force. Ny equal to mg, Nx must be providing the required centripetal force. If you want to find the total hinge reaction, that is the resultant of both. And sin theta is coming into picture. I know cos theta from here, so I can substitute it back. Now Cater's pendulum, there is nothing much important here. It's like if you can find 2 points, such that if you hang from this point and if you slightly move it and leave it, like it will be performing SHM. So you need to find two. So it's like if I hinge at this point, or if I connect at this point, and if I take the rod this way and if I leave it, it will be performing SHM. Similarly, if I take this thing, and obviously like center of mass will be coming down for stable equilibrium. So if I hinge it from this this particular point, and if I try to make it SHM, then it will be making some time period. So what we need to do is, we need to choose 2 points so that time periods will be same about those 2 points. So once we know that, then we can calculate acceleration due to gravity at that particular location, no matter where you go. If you go to moon, if you have Carter's pendulum, you can find acceleration due to gravity on the moon. So how it is going to be? So let me say I have hinged at this particular point. So when I leave it, when I take it and when I leave it, torque due to weight will be mg into L. This, let me call this length as LC. That is center of mass length from here, distance from here. Mg into LC into sin theta equal to moment of inertia about this axis, which is IC plus ml square into alpha. Now when the angle is small, sin theta will be almost equal to theta. Right. So it is of the form alpha equal to minus omega square theta, like SHM. This omega is not the rate at which theta is changing. This is SHM omega. So omega will be this much. So when you modify the equation, you will be getting something like this. It is a quadratic in LC. That is, you will be having 2 roots. What are those 2 roots? One root is this, one root is this. So summation of the roots is LA plus LB. So when I take summation of the roots, it will be something like this. Now from there you can find G value. G value will be how much? 4 pi square by T square into LA plus LB. So if you know those 2 particular points, you can calculate what is the time period, and you can find what is the length between them, and you can find the acceleration due to gravity. Anyway, that's not much important thing. So now going to the last one, it is like there is some circular object here. There is some okay. So okay, so there is some phone here. So let me say I am rotating it this way. I am rotating it this way. Now you can see like this is cam, right? So when I am rotating it this way, you are seeing the screen. You are seeing the screen, right? So I can visualize this motion in any motion. I can visualize it like motion off center of mass and motion about center of mass. Motion off center of mass and motion about center of mass. What is the motion of center of mass? Motion of center of mass is curvilinear. Curvilinear. So if I look at this motion, what is this motion? This motion is like this, right? You will be seeing the screen. So if I look at the motion like motion off center of mass, if I look at the motion like motion off center of mass, how it looks? Every time the phone looks in the same manner for you. So right now it is like this. In the next moment it will be like this, like this, like this. So every moment the phone looks the same, just the position will be different, right? So this is till here it is motion off center of mass, motion off center of mass. Now motion about center of mass, motion about center of mass. How the motion about center of mass is happening? It is rotating about this axis by 180 degrees. So you can look at this motion like motion off center of mass and motion about center of mass. Now that's the whole thing. Now if there is a rod here and there is a disc here, now if you are rotating, okay, I will show how it looks. So if there is a rod here and there is a disc here, and I marked points P, C and Q. So if I rotate it this way, what will happen? When it comes to this particular position, P will be here, C will be here, Q will be here. Now if I rotate further, then this Q will go here. Q will be here, C will be here, P will be here. Now this is what happens when you weld a rod and when you rotate a disc. But how you can see this motion? You can visualize this motion like motion off center of mass and motion about center of mass. Now how it looks like when I see like motion off center of mass, when this particular thing goes here. Now motion of center of mass means it looks the same way. P, C, Q must lie in the same line. So it looks like this. This is motion of center of mass. But actually what was happening when I weld it and when I rotate, what will happen? Actually Q has to come here and P has to come here. So I need to see what I am trying to do. I am trying to see this particular position as from here to here, the motion, whatever motion is happening from here to here, I am trying to see it as motion off center of mass and motion about center of mass. So I am trying to see this one as motion off center of mass and motion about center of mass. Motion off center of mass will look like this. This goes exactly like this, where PCQ will be in same line. But I need to see motion about center of mass also. So about center of mass, there will be a rotation of 90 degrees, so that you will be getting QCP in line. Now this is same as this particular situation. So we have seen this motion from here to here as motion of center of mass and motion about center of mass. Now similarly we will see the other position also, we will see this position also. So in order to see this position, what we can see, motion of center of mass, so that is PCQ will lie in the same line, PCQ, motion of center of mass, and motion about center of mass. How much angle you have to rotate about center of mass to get this position, how much angle you have to rotate from here? It is 90 plus 90, 180, right? So when you rotate 180 degrees, you will be getting this figure, which is same as this figure. So you can see the actual omega and omega about center of mass in this particular question is same. Actual omega, so actual rotation of this thing is 180 degrees for this position. So rotation about center of mass, when you are trying to see it like motion of center of mass and motion about center of mass, rotation about center of mass is also going to be 180 degrees. So omega is going to be same, right? Thank you.